Hey guys, in this video we're going to talk about Chapter 16, Section 2, Iterated Integrals. So our old friend from Calc 1 is back, the integral. And remember how, we came to this definition involving limits. The idea was to find the area under some curve, right? It doesn't matter, if the curve is really weird looking, as long as it was continuous, we had a way to do this. And the way to do this was with this definition, this limit definition of a Riemann integral. And basically what this is telling us, it has two parts to it, really. It has the height of a rectangle, of an infinitely small rectangle, infinitely skinny. And we had the width of a rectangle. That was delta x. And remember what this idea was. Well, we had these really skinny rectangles, right? That's where the limit going to infinity is coming in. These things are really skinny. And we had some delta x associated with each of these. That was the width. And the height was going to be this f of xi, right? And so the idea here is to let n go to infinity. So, in other words, make these rectangles super, super skinny so that we can fit infinitely many in here of the same width. And the idea was, hey, go ahead and sum all of these up, infinitely many skinny rectangles with the same width, and that's going to be our definition of the Riemann integral. And we did lots of examples with this in Calc 1. We also looked at different integration techniques in Calc 2, such as integration by parts. We looked at tables of integrals and things like that. So integration by parts is going to make a little appearance in today's lecture. We're not gonna get too crazy with the integration by parts, but we are gonna see it again in Calc 3. So let's talk about the key differences between integrating in Calc 1 and integrating now in Calc 3. So in Calc 1, we only had one independent variable x, and what that corresponded to is that the curves were in 2D. And what we were looking for was area under the curve, okay? So that was in Calc 1. Now what we're going to be doing in Calc 3, since we've been dealing with graphs of surfaces, so three-dimensional objects, we're not going to be finding the area under a curve, because here curve doesn't make sense. We're going to be finding the volume under a surface, okay? So what does that mean? Well, instead of summing up infinitely many rectangles like in the 2D case, we're going to be summing up infinitely many rectangular volumes of rectangular prisms. Okay, that's what we're going to be doing. We're going to be finding volumes of these skinny little rectangular prisms, and they're all under the surface right here. Okay, we're going to be adding them all up to find the volume under this surface. And notice that here we're gonna have two integrals, right? And I'm gonna explain what that corresponds to a little bit more in a second, but basically what we're gonna be doing is we're gonna be finding the volume of a rectangular prism with respect to x. So we're gonna travel along the x-axis, and we're gonna fix y. Okay, so we're going to travel along the x-axis from A to B, add up those volumes, fixing y, okay, whatever it may be, fixing y, and then what we're going to do is we're going to let y vary on an interval from C to D, and we're going to fix x, okay, and then we're going to sum up those volumes, and together what that's going to amount to is the volume under the surface. It's a pretty cool idea here. So here's the technical definition. Suppose a function f, okay, so we're thinking of a function as a surface, is continuous on a region. So remember, a region is just going to be, it could be a rectangle on the XY plane. It's something on the XY plane is what I mean by a region. So this is our domain here, okay? So suppose the function is continuous on a region. The rectangle from x is going from A to B, and y is going from C to D. If u sub ij, v sub ij is any point on the ijth sub-rectangle, we define the definite integral of f over r as follows. So this is, a pretty technical definition, but it's basically just saying what I said in this slide right here about summing up the volumes, right? So we're going to let delta x, delta y both go to 0. And what does delta x, delta y corresponds to? That corresponds to the length and the width of these rectangles, right? So we're going to let that go to 0. So we're going to let these things get really, really, really small. And then we're going to see what the height is, and that corresponds to f of u ij, vij. So we're going to look to see what that height is right here. And so we're going to take the area here of the rectangle downstairs, so that's delta x times delta y, and multiply it by the height, and that corresponds to the point on the surface. We're going to sum all of those up, and remember, guys, this is the intuitive idea here. The volume of a rectangular prism, or really you could say anything, the volume is going to be the area of the base times the height. This is the area of the base, delta x times delta y. So delta x is going to be the change in x, so going this way right here, and delta y is going to be the change in y. So that's, if we multiply delta x times delta y, that is the area of the base, and the height is just going to be, the z value. Basically, we're evaluating the function at delta x, delta y. So we're not going to be really using this technical definition much, but just to give you some insight on, what the parts of it mean, I think is important. If r is the rectangle, x varying from A to B, y varying from C to D, and f is a continuous function on r, then the integral of f over r exists, and it's equal to the iterated integral. So we have f of xy, which is our z value. So our surface as a function of x and y, we're going from x equals a, from x equals b, d, and we're letting x vary, but we're fixing y. We integrate that, and then whatever we get when we do that, we integrate it with respect to y. And we're going from y equals c to y equals d. You can also write it like this. That's how we're going to write it most of the time. And one important thing is that the order of integration does not matter. So you can integrate with respect to y first if you want to. In that case, this would be, we would have f of xy. Then we would go from c to d first, fixing x. And then on the outside, we would integrate with respect to x. So we'd go from a to b. Okay, so these two things are the same. So let's go ahead and do some examples. Okay, so one piece of awesome news, the news is full of terrible things, but one thing that happened recently is pretty awesome, and that is that Desmos came out with a 3D graphing calculator. It's amazing, y'all. We're going to throw GeoGebra out the window. Sorry, GeoGebra, but Desmos is the best, okay? So if you guys haven't checked out the 3D graphing calculator, please do. It's amazing because Desmos is awesome, very user-friendly. Just Google Desmos 3D calculator, it'll come up. Anyway, what I really like about the Desmos 3D calculator, that would have been super helpful when I was talking about Lagrange multipliers, is that you can actually restrict the domain in 3D here. Like, you can restrict X and Y, and it'll do that for you. It'll pop up on the 3D calculators. Pretty cool. So, anyway, with all that being said, look at this. We're trying to integrate from, first of all, we're going from X varies from 0 to 4, so I put that in here in Desmos. X is going between 0 and 4. And then we're varying from Y is going from 0 to 3, so I also put that in Desmos in the little curly braces. And the actual function that I'm trying to integrate is z equals 4x plus y, okay? So that's my surface. And you can see it on here. If you were actually in Desmos, you could turn this around, rotate it, get a feel for what it looks like. But that's what we're trying to find. We're trying to find the volume under this region, okay? So, you know, if you imagine that this thing is, you know, if it's some kind of what's the word I'm trying to say? Some kind of container, I guess. Like, how much volume would this hold? How much volume would that hold? That's what we're trying to do here. Okay, so here is the process. The first thing we're going to do is we're going to note that we are integrating with respect to x first. And when you do that, just like when you're differentiating in two independent variables, you're going to hold y constant first, okay? You're going to act like y is a constant number. So let's go ahead and get this going. So let's go ahead and integrate this first with respect to x. Remember how we did that in Calc 1. Now this, we know how to integrate with respect to x from Calc 1. We have 4x squared over 2, right? Now this guy is just a number, okay? We're holding y constant. So to integrate that with respect to x, it's just plus 3yx. Just like if you had 3 and I was trying to integrate with respect to x, it would be 3x. It's the same idea, y'all. Y is fixed, okay? So we're treating it like it's a constant. Okay, and my bounds, we're going from 0 to 4, and then on the outside, I'll just carry everything else over. So let's go ahead and evaluate this. Remember, we're doing this with respect to x, so we're plugging in the numbers for x. So what I get when I do this is, well, first of all, this can simplify to 2x squared plus 3yx. We're going from 0 to 4. So when I plug in 4, I get 2 times 4 squared plus 3y times 4 minus, and then I'm going to plug in 0 for x. 2 times 0 squared plus 3 times y times 0. And of course, I ran out of room, but there's a dy on the outside there that I haven't taken care of. So let's go ahead and simplify this. What's nice about this is that this all goes to 0. And so we're left with, we're integrating from 0 to 3. Let's see, this becomes 32 plus 12y dy. Okay, now we have to integrate with respect to y, and we know how to do that. That's just going to be 32y plus 12y squared over 2, and we're going from 0 to 3. Alright, so this is going to be 32 times 3 plus 12 times 3 squared over 2 minus, and then all of that is just a bunch of junk that's going to go to 0. We plug in 0 for all of this. Hopefully you guys can see that's going to be 0. Okay, now let's get out the good old handy dandy calculator and see what this evaluates to. So we have 32 times 3 plus, let's see. Okay, so I'm getting 150. Now what is this? This is going to be units cubed, right? Because this is volume. We're trying to find the volume under the surface bounded by this rectangle below, okay? Alright, so that was our answer there. Let's go ahead and do some more examples here. Alright, so see how much I love this calculator. This is way better than GeoGebra. I mean, Desmos just does it right, you know? It's like, I know you guys that are watching that are hardcore, like, Microsoft fans. I am an Apple person. I love Apple. I think it's so efficient, so clean. And that's how I feel about Desmos. It's just... it's just awesome. Okay, so let's go ahead and evaluate the integral. So let's check out what's happening first. Now we're integrating with respect to y now first, right? Because of that dy is coming first, where before we were integrating with respect to x because the x came first. But now we're going with y. So now we're treating x as if it's a constant, okay? So when we integrate this guy with respect to y, okay, so now x is a constant. So 6x, that's just a number, okay? You just want to think of it as a number. So how would I integrate this? This would be 6x y squared over 2, right? We're integrating with respect to y first. We're going from 0 to 2. And then on the outside, we have that dx from 0 to 3, okay? Remember, 6x is a number. The x is a number. It's not a variable. We're holding x fixed when we integrate with respect to y. Okay, so if I simplify this, this becomes, let's see, 6 divided by 2 is 3, so we have 3x, y squared, 0 to 2. And if I now I'm plugging in the y because I integrated with respect to y. So I get 3x times 2 squared minus... That's going to go to 0. Okay, fine. Alright, so 3x times 4 is 12x. So I'm going from 0 to 3, 12x dx. Now I just need to integrate this guy with respect to x. So this is going to be 12x squared over 2 from 0 to 3. And that's going to be 6x squared from 0 to 3. So 6 times 3 squared minus 0. 6 times 0 squared is 0. And I get 54. So that's my answer. Remember, this is volume. So this is going to be units cubed because we have volume that we're trying to find. So this was the volume where the bottom of this prism or surface or whatever you want to call it is bounded by this rectangle, x going from 0 to 3, y going from 0 to 2. So we just found the volume under that surface. Okay, so we want to sketch the region of integration and evaluate the integral. Okay, so our region of integration is told to us by these bounds, and which one comes first over here. So since y is the innermost, since dy is on the inside, this guy corresponds to the y bounds. And since dx is on the outside, this corresponds to the x bounds. Alright, so y is between 0 and 4, and x is going to be between 1 and 3. So this is a rectangle, and we can sketch it if we want to. So x is between 1 and 3, and y is between 0 and 4. Maybe I'll do this in purple. It's going to look something like this. So y is between 0 and 4, height of 0 up to 4, and x is going to be between 1 and 3. So this is where we're integrating on. This is our domain, essentially. And let's go ahead and do this. So the first thing you want to notice is that this might be hard to integrate unless we employ a little trick. So the trick is the power rule for exponents. Well, not the power rule from calculus, but the power rule from algebra. So multiplication of exponential terms. If we have e to the x times e to the y, that's the same thing as e to the x plus y, right? That's what I mean. So I can just replace e to the x plus y with e to the x times e to the y. Alright, so that's going from 0 to 4, from 1 to 3. we're integrating with respect to y first, which means we're holding x constant. So, since we're holding x constant first, isn't it true that e to the x is just constant? Right, because e is constant, x is constant, so e to the x is constant. Therefore, we can pull it out just like we would with a constant number. So we would have e to the x on the outside, going from 0 to 4, e to the y dy. And then we know with e to the y, the integral is just e to the y. So we get e to the x on the outside. And then we have e to the y evaluated from 0 to 4. So we're taking care of this first. So e to the y from 0 to 4 is going to be e to the 4 minus e to the 0, and still this is all being multiplied by that e to the x on the outside. And e to the 0 is 1, so we have 1 to 3 e to the x times e to the 4 minus 1. And now we can integrate this guy with respect to x. So notice that e to the 4 minus 1 is a constant. Right? It's just a number. So we can pull it out to the front. So we have e to the 4 minus 1 on the outside. Then we're going to integrate from 1 to 3 e to the x dx. Now, of course, when you integrate e to the x, it's just e to the x. So we have e to the 4th minus 1 times e to the x evaluated from 1 to 3. So then we have e to the 4 minus 1 times e to the 3 minus e to the 1, which is just e. And that's it. That's your answer. Okay, so let's see. Let's look at this one. So we want to sketch the region of integration and evaluate the integral. Okay, so it looks like y is first, and says y is going from x to 2x. So y is between x and 2x. And then our second piece tells me that x is between 1 and 5. Right, because this is the outer one right here. Alright, so if I sketch what this looks like, so y is between x and 2x. Alright, so we have two lines. We have the line y equals x and y equals 2x. So y equals x is going to be something like this. Well, actually, maybe I'll make it a little less steep. So y equals x is our lower bound here. And then y equals 2x is going to be slightly steeper. This is y equals 2x. Alright, so that's my y bounds, is bounded between those two lines. And then for my x bounds, I'm going from x equals 1 to x equals 5. So if I kind of just like draw this like that for x equals 5, and then like this for x equals 1, I see that the region enclosed by these is going to be this guy right here in gold. Okay, so that's a very rough sketch of the region. Now let's go ahead and integrate this thing. So we're doing this with respect to y first, so that means that x is constant, which means that, you know, if you think of x as a constant, the sign of a constant, I mean, it's just a number, right? So if I integrate this with respect to y, I get y sine of x, right? X is constant. We're just thinking of sine of x as like a number. And we're going from x to 2x. And then we still have the 1 to 5 on the outside dx. Okay, so hopefully this makes sense why that is this. Sine of x, it's just like what if you had sine of 3? Right? X is just a number. It's held constant because we're integrating with respect to y. This is just a number. And remember, when you integrate numbers, you just tack on the variable that you're integrating with respect to it. Okay. So let's go ahead and evaluate this guy on the inside. So since we integrated with respect to y, we're going to plug in these bounds into y. So we have 2x sine y. Or sorry, 2x sine x is what I meant. Minus x sine x. And I can combine like terms here before I integrate again. So 2x sine x minus 1. X sine x is just x sine x. And here our integration by parts needs to come into the picture because we can't really integrate that directly. I don't know a way to do it. So we have to use integration by parts, which we all know and love. So integration by parts is when you have a product that you're trying to integrate. And that's the case here. So we have the integral of u dv is equal to uv minus v du. And remember, we chose what we picked as u and dv. And typically, u was going to be the simpler thing to take the derivative, or the thing when you take the derivative of, it's the simplest one. So I'm thinking we should make u equal to x. And so when I take the derivative, I get du is equal to dx. And so that leaves dv has to equal sine x dx. Okay, so dv is equal to sine x dx. And so v is just going to be negative cosine x when I integrate this guy. Okay, so now that I have all of this information, I can go ahead and use my formula, right? This is u, this is dv, and so that's going to equal the right side of this equation. So this is going to equal, so we're going from 1 to 5, and we have u as x, so here we're going to have x times negative cosine x, which is negative x cosine x, minus, we're going to integrate v, which is negative cosine x, times du, which is dx. We can pull the negative out in the front, and that's going to give us negative x cosine x plus cosine x dx. And we're evaluating this, again, from 1 to 5. So before I do that, let's go ahead and get rid of this integral. You integrate cosine of x, you get sine of x, right? Because the derivative of sine of x is cosine of x. So we're going to get negative x cosine x plus sine of x, and we're going from 1 to 5. So we have negative 5 cosine 5 plus sine of 5 minus negative 1 cosine 1 plus sine of 1. So if I just clean it up a little bit, I get plus cosine 1 minus sine 1. And that is my answer there. So that is integrating this guy. Alright, so we want to sketch the region of integration and evaluate the integral. Alright, so it looks like our x, our dx is on the inside, so this guy corresponds to x. So we have x is between y and 3y, and then this guy's going to correspond to our y value since he's on the outside. So y is going to be between 1 and 2. Alright, so let's go ahead and do a little sketch of this. So y is between 1 and 2. So here's y equals 1, and here's y equals 2. Let's kind of like draw a dotted line to say we got those bounds. Alright. And so x depends on y. So x is between y and 3y. So if I plug in my lower bound for x, I get, so like when y is 1, that's what I mean. When y is 1, I get x is between 1 and 3 times 1, which is 3. Alright, just using that. So, okay, so here's x equals 1, so maybe that's right here. So x is between 1 and 3 when y equals 1. So maybe like right here. And then when x is equal to 2, or sorry, when y is equal to 2, I have x is between 2 and 6. So here's x equals 2, maybe x equals 6 is somewhere over there. So when y equals 2, we have something like that. Something like that. And then we can just connect the dots and get this sort of shape right here. Kind of trapezoid looking. Okay, so there is our region. Now let's go ahead and evaluate the integral. So first of all, we're integrating with respect to x. So we are holding y constant. And so if I integrate this guy with respect to x, holding y constant, I get x squared over 2y. And I'm going from y to 3y. Alright, so if I plug in the 3y for x, I get 3y squared over 2y minus y squared over 2y so cleaning that up on the inside, I get, let's see, 3y squared is 9y squared over 2 times y is 9y to the third over 2. And then we just have minus y to the third over 2 for this piece right there. Alright, so let's go ahead and integrate this guy with respect to y. So when we do that, we get 9y to the 4 over 4, right? Because 2 times 4 is going to give us 8, so that's how I got that. Minus y to the 4 over, again, 2 times 4 is going to give us 8 down there. And we're going from 1 to 2. Okay, so we have 9, 2 to the 4th over 8, minus 2 to the 4th over 8. Well, actually, let me go ahead and combine this before I plug in my limits. This is just going to be 8y to the 4th over 8, which is just y to the 4th. So if I plug in my limits now, this is going to be 2 to the 4th minus 1 to the 4th. And that's going to give us 15. And that's our answer. Okay, so we want to write the integral f of dA as an iterated integral for the shaded region R. So we have a rectangle here, right? And so what we can see from this region is that x is varying from 1 to 4 and y is varying from 1 to 2. Okay, so if I write this as an iterated integral, We're going from 1 to 4 in the x direction, and we're going from 1 to 2 in the y direction. And this is going to be f dx dy. All right, x is coming first because that is given by our inner bounds there. So this guy would be our iterated integral. All right, so we want to write this integral as an iterated integral for the shaded region R. So we need to put some bounds on x and y to describe this region. So for x, we can see that, anything that's shaded starts at x equals -1 and ends at x equals 3. So we're going from -1 to 3 in the x direction. What about the y direction? Well, we can see that the lower bound for y is -2, but y is bounded above by this line right here. So we need to figure out the equation of that line because that's the upper bound for y. So we're going from -2, so that's the lower bound to y, and the upper bound, y is bounded above by this line right here. So what's the equation of that line? Well, let's go ahead and look at these 2 points that are on the line, right? Because we just need 2 things for a line. We need the slope and we need the y-intercept. So let's figure out the slope of this line using these 2 points. So here our ordered pair is going to be x equals 3, y equals -2. And up here, our ordered pair is x equals -1 and y equals 1. So our slope tells me to do y minus y over x minus x. And when I compute this, I get -3 over 4. So that's my slope. Now for the y-intercept, okay, so we got the slope figured out. For the y-intercept, we can pick any point, right, and just plug in x, y, and m into this equation and solve for b. So I'll just pick this point. You could have easily called this one x comma y, but it doesn't matter. You just need a point. So here, x is -1, y is 1. So we have 1 equals, and then our slope we found was -3 over 4. So we have -3 over 4 times x plus b, and we're going to go ahead and solve for b. So we have 1 equals 3/4 plus b, subtract 3/4 from both sides, and we're going to get 1/4. So b is equal to 1/4. Alright, so this is going to be, our upper bound is going to be the line, -3 over 4x plus 1 over 4. So that is how this thing is bounded above in the y direction. Okay, and then of course we're going to we don't really know what function we're integrating, but we can still put f. And then so this guy is our y bounds. This is bounding from below and above, so this is going to be dy comes first, and then our outer bound was x, so that's going to be dx. And that is our answer there. Alright, so let's find the volume of the solid that lies under the paraboloid z equals x squared plus y squared and above the region R bounded by the line y equals 2x and the parabola y equals x squared. Alright, so we need to set up our integral some kind of way. First of all, we know that f is just going to be x squared plus y squared because they tell us that that's the surface, right? We're trying to figure out the volume of, that lies under this surface, right? And you can explore this on Desmos, on the new 3D calculator. But anyway, this is what we're trying to integrate. Now the tricky part sometimes is figuring out what the bounds are. Okay, so figuring out what the bounds are. So we know what the bounds are for y. We have 2x and x squared. And so, what this looks like if you were to plot this. So we have y equals 2x right here. And y equals x squared is gonna meet 2x somewhere right here. Alright, so this is y equals x squared. This is the point 0, 0. And this is the point 2, 4. Okay. So we can see that the lower bound here is x squared and the upper bound is 2x. So we're going from y is equal to x squared is my lower bound and 2x is my upper bound. I'm integrating x squared plus y squared, and I'm going to do it with respect to y first. Now, what are my bounds for x? Well, that's when you would see what the intersection of these guys are. So if we set these guys equal to each other, we get 2x is equal to x squared. Now, if I subtract 2x over from both sides, I get x squared minus 2x equals 0. And I can go ahead and factor out an x at this point. So I get x times x minus 2. And if I set each of these guys equal to 0, I get x equals 0 and x equals 2. And that agrees with our picture here. So in the x direction, we're going from x equals 0 to x equals 2. And this is going to be our little region right here. So in the x direction, we're going from x equals 0 to x equals 2. And now let's go ahead and integrate this thing. So we're going with respect to y first. So we want to integrate this with respect to y. And remember, when we do that, x is treated like it's a constant. So if I integrate this thing, so x is a constant, so if I integrate it with respect to y, it's just going to be y x squared, right? Just like you would integrate any constant, plus y to the third over 3, and we're going from x squared to 2x. And then I'll put this on the outside. Let's see. So then I'm going to go from 0 to 2 in the x direction. Okay, so let's go ahead and put this in our bounds in. And remember, we're putting our bounds in y because that's what we integrated with respect to. Okay, so we have 2x times x squared plus 2x to the third over 3 minus x squared times x squared plus x squared to the third over 3. I'm just plugging my bounds in there. And I'm going to clean it up a little bit. And then I still have this thing as being integrated. Okay, sorry guys. I had to redo this because some wire came disconnected, the audio wire. Anyway, this is where we were. Okay, so let's go ahead and clean up this mess a little bit. So 2x times x squared is going to be 2x to the third. Alright, this guy is going to turn into an 8x to the third over 3. Okay. In here, we get negative x to the fourth when we distribute the negative. And then this is x to the 6 over 3. So this is going to be negative x to the 6 over 3. And let's go ahead and maybe we should combine like terms before integrating. So let's see. So we have x to the 3 minus 2x to the 3. So that's 2x to the 3 is 6 over 3x to the 3, right? Just finding common denominators. So this is going to turn into 14 x to the 3 over 3. Alright, so let's go ahead and integrate this with respect to x. Alright, so this is going to be 14x to the 4 over 3 times 4, right? I'm just putting the 4 under there. Minus x to the 5 over 5 minus x to the 7 over 3 times 7 is 21. And I'm going from 0 to 2. The 0, that's all going to clear. And I'm erasing this because I did this earlier on here just to do it for the first time. But let's go ahead and compute this. Okay, so we have 14, 2 to the 4th over 12, minus 2 to the 5th over 5, minus 2 to the 7th over 21. Let's see, what did I get down here? Let's see. And then let's see what this is. So we have 14 times 16 over 12 minus 32 over 5. Let's see what Desmos is going to give me when I do this, or what my graphing calculator is going to give me, because I am old-fashioned. I have this, let's see, TI-84 plus silver edition. It's basically a fossil from prehistoric times. So let's see what I get here. Okay, let's see. My least favorite part of math is like the arithmetic. I don't know about you guys, but I hate, like, I always make arithmetic errors. And I'm always like, please come out to be the answer that it's supposed to be. Let's see. Minus 128 over 21. Okay, I think it is coming out to be the answer that's supposed to be. So I'm getting 216 over 35. And this is the volume, okay? We're not really sure what the units are because the units weren't specified. But if you were to tack on some units to it, it would be units cubed, okay, since it's not specified in that way. Alright, let's go ahead and do this one. This is kind of fun, right? So we're going to find the volume of the given solid under the surface, z equals xy, and above the triangle with these vertices. Okay. Alright, so this is the region that we're integrating on, this triangle. This is our domain, essentially. So I guess we can sketch it and then do our bounds that way. So, right, because our bounds comes from the region, our x and our y bounds. Alright, so here's our x-axis, here's our y-axis. We have a vertex at 1, 1, so x is 1, y is 1, fine, there it is. X is 4, y is 1 is our next one, so 2, 3, 4, so right there. And then finally we have x is 1, y is 2, so right there. So here's our little triangle region. So this is what we're integrating on, and we're trying to find some bounds for this region. So this is pretty similar to what we've done before. We can see what our x bounds are pretty easily. It's bounded to the left by x equals 1, and it's bounded to the right by x equals 4. So those are going to be our x bounds from 1 to 4. So what about y? Well, we can see that y is bounded below by y equals 1, and it's bounded above by this line right here that we're not sure what the function is for that. So we're going from y equals 1, and now we need to figure out what this line is. Well, this line has an ordered pair of 4, 1 right here, and then up here we have an ordered pair of 1, 2. So let's go ahead and find the slope. So slope, we have y minus y over x minus x. So it's going to be negative 1 over 3. So that's our slope. And then to figure out our y-intercept, we just do the same thing that we did in a previous problem. So we have y equals mx plus b. I'm going to choose x as 1, y as 2, but you could have easily chosen that one as well. And I'm going to plug in my x and my y values. So we have 2 equals negative 1 over 3 times 1 plus b. So we get 2 equals negative 1 over 3 plus b. And if I add 1 over 3 to both sides, I get b is equal to 7 over 3. So my line is y equals negative 1 over 3x plus 7 over 3. So this guy is bounded above in the y direction by negative 1 over 3x plus 7 over 3. Okay, so those are my bounds, and that's always the hard part, is finding the bounds. And then the function that we're integrating with respect to is just x, y. We chose to go in the y direction first, so this is, right, because those are y bounds from below and above. So y bounds. So we have dy on the inside, dx on the outside. So let's go ahead and integrate this guy with respect to y first. All right, treating x as if it's a constant. So when I do that, I get x y squared over 2. And we're going from 1 to negative 1 over 3x plus 7 over 3. So that's my inner integral, and I still have dx on the outside from 1 to 4. Okay, so let's go ahead and plug in these bounds for y. So we get x times negative 1 over 3x plus 7 over 3 squared over 2 minus x times 1 squared over 2. And now I have to do a little bit of work, which I'm not happy about, but oh well. Okay, so we have to FOIL this thing right here. Let's go ahead and do it. Okay, so first, outer, inner, last, we get 1 over 9x squared, and then minus 7 over 9x, minus 7 over 9x, plus 49 over 9. Okay, so this is 1/9 x squared minus 14 over 9x plus 49 over 9. And so that was this part, but then that x is going to distribute, so I'm just going to take care of that real quick and distribute that x in there. So let me rewrite this. I'm going from 1 to 4, and I have 1 over 9 x to the third minus 14 over 9 x squared plus 49 over 9 x. And this is all divided by 2. So, like, basically I'm just multiplying these denominators by 2 if I want to clean that up. So this is going to be 18. Well, wait, let's go ahead and let's leave it for a second. Let me go back. Let's just leave it how it was. And then here we have minus x over 2. Okay. And I'm not putting my dx, but hopefully you guys know it's there. Okay. So let's go ahead and I guess we can combine these like terms. Alright, so we have 49 over 9 minus 1 over 2. And I'm getting 89 over 18. Beautiful numbers here. x to the 3 over 9 minus 14 over 9 x squared plus 89 over 18x. This is all over 2, and now I can go ahead and get rid of that 2 in the denominator by just simplifying. Okay, and let's go ahead and integrate this. So when I integrate this, I get x to the 4 over 18 times 4 minus 14 over 18 x to the 3 over 3, so times 3 on the bottom, plus 89 over 36 x squared over 2, and we're going from 1 to 4. So when you plug in these bounds, what you should get at the end of the day is 31 over 8.